Welcome class, thank you for joining me for your 2.6 notes. Today we're transitioning a little bit and we're going to be talking about families of functions. So our objective is to analyze transformations of functions. How can we take a simple function and change it to either reflector or translator or anything of the sort? So the first vocab word I'd like you to know is a parent function. So a parent function is the simplest form in a set of functions that form a family. Each function in the family is a transformation of the parent function. So for example, a parent function would be the parabola x squared. And then we can do certain things to that function, do transformations in order to change it and create every other type of parabola. So let's get started with what are these different types of transformations. The first one I want you to know is a translation. A translation shifts the graph of the parent function horizontally, vertically, or both without changing the shape or orientation. For positive k, parent function f of x plus or minus k is a vertical translation. For positive constant h, the function x plus or minus h is a horizontal translation. Now, let's get a visual of what that means because that's really wordy, a little bit difficult to take in. So let's get a visual of this. So red in both of these pictures is going to be my parent function, okay? Now, on the vertical translation side, I want you to notice here, you are adding something at the end. You're taking your function and you're just adding on to it at the end, okay? Or subtracting from the end. So what does that do? You take the function and you either perform the function and then add something, perform the function and subtract something. Well, that is how you're getting your motion up or your motion down. So that's how you need to remember vertical, is any vertical shifting, any shifting along the y-axis, just add or subtract at the end, okay? Add or subtract separately from everything else. Now, for a horizontal translation, again, the red is going to represent the parent function. Now, I want you to notice how they're representing it here. This time, that value is being added and subtracted from the x itself, okay? So, that is what's creating our horizontal change. And again, horizontal being the x-axis, so really it makes sense that these changes occur in the x itself. Now, I do want you to notice something. It's a little bit backwards from what we would be expecting, because notice, subtracting moves it to the right, and adding moves it to the left. So for these horizontal changes, when you're taking or adding from the x, you're actually getting the opposite motion from what you would probably be expecting. So that's the next thing I need you to remember is for horizontal translation. I want you to think of opposite, or if you look at that little hint there, how this is a tricky concept. It seems backwards. Look at the picture to the left. What is h? The horizontal graph f of x is either shifted one to the right or one to the left. Therefore, h is 1. This only changes the x value for the input, not the y value you get for the output. Okay? So again, try to keep that straight. You're going to have to think opposites. Now, if you jump below, here's a t-chart for the input and output values. Now, note both of these are coming from this graph. Okay? So, here is going to be our f of x over here. All right? This table of values. So on this one, you plug in 0, you get 0. You plug in -1 or 1, you get 3. Now, we're going to shift this, okay? So I want you to notice what happens. So here, all of the y values are the same, okay? So the y values haven't changed. It's the x values that are changing. Notice here we have -1, 0, and 1. Here we have 0, 1, and 2. So I want you to notice, when you plug in 0 to this one, you get the same result as plugging in -1 on the red one. When you plug in 1 on this one, you get the same thing as when you plugged in 0 on the last one. So this transformation, to relate it to the parent function, what's happening is we're taking every x value from this one, and when we subtract 1, we get the same thing as the red function. So here you can see we are shifting our x's, okay? And again, it makes sense because we already talked about how that negative means we're shifting to the right, which you can see -1 to 0, 0 to 1, 1 to 2. That's why that's happening, okay? So that minus sign is shifting all those x's 1 to the right in this function. All right, so let's take a pause here and think about what we're doing with transformations. So let's summarize these translations at least. What transformations take place to change the parent function, f of x, into that? F of x plus 3 minus 1. I'm going to focus on the x plus 3 first, okay? So notice this is a change happening with the x. The x itself is being changed. So that means that is going to be a horizontal translation. Now also remember that for horizontal translations, the opposite of what we're thinking is happening. So that x plus 3 is actually 3 to the left. All right, again, opposite of what you're probably expecting would have happened. Next piece, at the very end, we're subtracting 1. Now remember, when something is being added or subtracted at the very end, this is a vertical translation. And a negative here does exactly what you would expect it to. You're going to move that parent function down 1. All right, so there's a nice little summary of how translations can affect a function. So let's continue on. The next thing we're going to cover are reflections. So a reflection flips a graph of a function across a line, such as the x-axis or the y-axis. Each point on the graph of the reflected function is the same distance from the line of reflection as its corresponding point on the graph of the original function. When you reflect a graph on the x-axis, the x values change sign and y values stay the same. When you reflect a graph on the x-axis, the x values stay the same and the y values change sign. So here, this one represents our parent function. So what I want you to notice is when we flip across the y-axis, I want you to notice all of the y values have stayed the same from the original, but the x values have flipped sign from what they used to be. Now, same thing down here, if we are going to reflect it across the x-axis, this time the x values are what stay the same from the original parent function, and the y values end up flipping their sign. Now, I want you to circle or highlight this because that is going to be what helps us understand how to make these reflections. So for the function f of x, the reflection across the y-axis means you're changing your x values. Across the y means y is staying the same, so it's the x values that are being altered. A reflection across the x-axis actually changes the whole function. It changes the whole y of the function. okay? So that's going to be your little tidbit here to properly do reflections. So I want you to highlight that. And now, let me show you what ends up happening. So, what would the new function look like if you reflect over the y-axis? So here's our parent function, okay? So across the y-axis. So again, I want you to look back up at this box. Use that box as a reference to help you keep this straight. So across the y-axis, all you do is you put a negative in with the x. So you actually end up just getting that. That is your new function, your reflected function, because over the y-axis, you only change the x. Now, the second piece, reflecting over the x-axis. Well, for that, we're changing the whole function. So there we're taking the opposite of that whole thing. And we end up getting that. So notice the difference. It's a very slight difference, but these give us two different things. All right, and again, very important, when you're practicing this at first, please, please, please be referencing that little box head you just make so it's easier for you to see how these things are changing. Vertical stretch is going to be our next one. Now, stretch implies it's getting bigger. Vertical compression implies that it's getting smaller, okay? So if we're thinking stretches, now, what that means, a vertical stretch means you're multiplying by something greater than 1. Vertical compression means you're going to be multiplying by a fraction. It's going to be getting smaller or shorter, okay? And you can see all of that in this diagram here. If blue is our normal, blue is our parent function, well, that means red is our vertical stretch. It's getting bigger. And then green is our vertical compression. It's getting smaller. Now to look at this in a table form. So notice we have the same x values in both tables. All right. However, notice the y values. What's happening with them? Well, for the same x values, that g of x is is multiplying by 3. Okay, so basically, in order to get g of x, what are we doing? We're taking all of those f of x values and we're multiplying them by 3. So now to keep straight, which one of these are we talking about? Well, we're multiplying by 3 and we're greater than 1. So this is going to be one of those vertical stretches. G is going to appear bigger than f. All right, describe the transformations of f of x that produce g of x. All right, now for this, I'm going to scroll down a little bit first because this may help you. This table here summarizes everything that we just talked about. So vertical translations, horizontal translations, vertical stretches and compressions, and reflections. So all of those things are summarized right here. So as you're doing your practice work, I'd recommend please have this out because you'll be able to reference this to help you figure out where to put what. Now, going back to the problem that we're being asked. Describe the changes that are happening. All right, so parent function. We're starting with this 2x squared. And we're getting this 4x minus 1 squared plus 5. Now, the first thing that I'm noticing is here, we're starting with multiplying it by 2, but now we're multiplying it by 4. Okay, so where it's multiplying, that parent function has changed. So that's going to be where I start, okay? So What's happened? Well, we went from 2, by multiplying by 2 to multiplying by 4. So that means that the new function is twice as big, all right? So twice as big, that's going to go under our vertical stretch. So I'm going to say that there is a vertical stretch of 2. It's being multiplied by 2. The next thing I notice is that right there, okay? So the x itself is being subtracted from. So what does that mean? Well, that's referencing this, right? The x itself is being changed. So that's going to be a horizontal translation. Horizontal translation of what? Well, it's being subtracted from, so we can see, oh, subtraction means to the right. So we're going 1 to the right. And then the last thing I noticed, this plus 5 at the end. And that is looking like that to me. We're adding something on at the very end of the function. So that's going to be a vertical translation. And what is it doing? Well, we're adding 5, so it's going to be vertical translation up 5. So that's how you can use the table. Look at everything that is being done to the function and relate it to a piece in that table to describe what that change actually means. All right, so last problem here. Find 4 points on the graph of y equals 3x minus 6. How those 4 points look after a reflection across the x, vertical compression of 1/3, translation of 3 right, and translation of 2 up. So what I'm going to do is I'm going to leave this as kind of food for thought for you, okay? This last one, I want you to think through that table that's still showing, and I want you to find any 4 points on the graph, and I want you to play around with this, okay? I want you to see if you can manipulate it and change those 4 points with those following transformations. At the beginning of class, we will talk through this, but I want you to give it a shot first. All right, so thank you for joining me for these notes. Please make sure you have everything written down, and then think about example 5 for me for us to discuss in class together.